This is Module 2, Lecture Notes 4. Today we're going to be talking about heat and the heat equation. You will need a calculator for this as well as your note sheet. So back in Module 1, we talked about heat, and we said that the way to measure heat is actually to measure the temperature of an object. If that temperature of the object begins to go up, we know that the object is absorbing heat from some source. Okay, and on the flip side, if the temperature of an object is going down, that object must be releasing some heat or losing heat. Okay, so we know that heat and temperature have a direct relationship, and there is an equation for that. Okay, let's break this equation down into the different variables. This letter Q will represent heat, and heat is measured in calories, so you can abbreviate it CAL. Okay, we said that heat is going to be proportional or directly related to the temperature. So that's this T over here. In front of the T, you're going to see a sign. It's the Greek letter delta. Okay, it's going to be related to the change in temperature. And change in temperature would mean that you have your final temperature minus your initial temperature. The temperature it ends at minus the temperature it begins at. Final minus initial. And the units for temperature are going to be degrees Celsius. Okay, the other variables you're going to see in your equation are M for mass. And what do we measure mass in? Grams. And the last variable is something called specific heat. Represented by the letter C. The specific heat of an object is going to be a standard value that is known, that is calculated, that's been tested. It will be a value that is given to you in each problem. It's not something you need to memorize or anything like that. You just need to know where to plug it in and kind of what it means and how to relate it to the other variables, but that will be given. Okay, so overall we have heat is related to the mass of an object times the specific heat times the change in temperature. Okay, so let's talk a little bit more about this specific heat value. Okay, specific heat is the amount of heat needed to raise the temperature of 1 gram of a certain substance by 1 degree. Okay, different materials have different specific heats, meaning it takes a different amount of heat in order to raise the material of an object depending on what it is. And I think you've probably experienced that. We all know from experience that if you stick a metal spoon in hot water, it's going to feel hot pretty quick, versus if you were to stick a plastic spoon in hot water, it would not feel as hot. So we've definitely experienced this, and now we're going to be able to use it in some actual calculations. Okay. I also like to think of specific heat is how easy is it to heat up a substance. Okay. So what I wrote here was a lower number or a lower value for specific heat means it's easier to heat an object up or to cool it down when it's made out of that substance. Okay, let's look at this and make sure that it's right. Something like copper. We know copper is a metal. It has a very small value, something much less than 1 for its specific heat value. It's going to heat up really easily. It's a metal. Same thing for iron. Okay, but what about like a styrofoam cup? Look how high the value is for specific heat. You could put hot chocolate in a styrofoam cup, and you could hold the outside of the cup, and you may not even ever feel that there's a hot substance in there. Styrofoam does not heat up very quickly. Okay? The units for C, or specific heat, are going to be in calories per gram degrees Celsius. And that just comes from these other variables in the equation: calories, grams, and degrees Celsius. So we can write that here. Okay. I want to give you a couple everyday examples that relate to specific heat before we get into some of these practice problems. Okay, I want you to draw a piece of pizza. You can have that in your notes, that way you can remember what we talk about here. So let's say you grab a piece of pizza and you stick it straight in your mouth, and it is burning hot. It burns your tongue. Which part of the pizza is actually burning the roof of your mouth? It's probably the sauce or maybe the cheese, but it's usually not the crust, okay? Substances that have a lot of water content tend to stay hot for a really long time because the specific heat of water is so high, meaning it's easy to heat up the sauce and the cheese because it has a lot of water in it, and it also takes a long time to cool down. Okay, so maybe think sauce stays hot because of the amount of water in it. Foods that contain a lot of water tend to stay hot for a very long time. The other type of food that will probably help you remember this is a bowl of soup. Okay, the broth of soup is mainly made out of water. Okay, so you heat it up in the microwave for several minutes. That soup is going to stay hot for a really long time because it has a very high specific heat. It contains a lot of water. So once it's hot, it will remain hot for a long time. So hopefully that kind of helps you think about these numbers for specific heat. Okay, let's jump into a practice problem. It says we have a 5-gram piece of copper and a 5-gram piece of iron. So we have copper, we have iron. Those are the symbols for them. They're the same size, they're placed on the same burner, and after 3 minutes we're going to measure the temperature. And the iron's temperature is 100 degrees Celsius. And we want to know, is the copper going to have a higher temperature or a lower temperature? Okay, so this is kind of a thinking problem that's going to relate back to the specific heat values found in this table. Okay, which one of these elements has a higher specific heat? Copper or iron? Iron has a higher specific heat. So that means that copper should actually be easier to get the temperature up. Okay, so the way that we will answer this question is we'll say that copper would actually be more than 100 degrees at this point because it takes less heat in order to raise the temperature of copper because it has a lower value for the specific heat. So I wrote that copper will be more than 100 degrees because it has a lower specific heat. Remember, lower number means it's easier to heat it up, and it's also really easy to cool down. So just relating these back to their values, we would make this assumption. Okay, let's jump into a problem where we're going to plug our numbers into our heat equation. We're going to cook an egg. It says our skillet has a mass of 500 grams. Also note that they tell us what it's made out of. That will be important to know which type of material to use for our C value. The skillet is going to be heated from 25 degrees Celsius to 150. So here's where we will find our change in temperature. The change in temperature is always going to be your final temperature minus your initial temperature. And we want to know how much heat is needed to do this. So I think we have everything ready to plug in. We're going to say our heat is equal to our mass times C. We go up here for iron. We're going to put in 0.108 times our change in temperature, which is 125 degrees Celsius. Okay, you'll grab your calculator and you'll punch that in. And I get 6,750. It needs a label. You could try to remember that heat is always measured in calories, but if you want to cross out your units, grams, grams, Celsius, Celsius, we are left with calories for the unit on our answer. Okay, our last problem is going to ask us to solve for another variable in the equation. Okay, it says if a 16-gram object, that's its mass, requires 70.4 calories of heat, that's our Q value, we're going to raise its temperature by 22 degrees Celsius. So they don't tell us the temperature it begins and ends, but they tell us how much the temperature is going to change by. That's going to be our delta T. What is the specific heat? So we're going to solve for C this time. Let's write out our heat equation since we can't see it up here on my paper. Q equals MC delta T. We can start plugging in what we know. The heat, 70.4 calories, is equal to the mass times, we don't know C, but we do know the change in temperature. Okay. This is really one of the first algebra problems we've solved together. If you want to get C by itself, remember you need to divide these over here to get C alone. So that would look like this. Divided by, that way we have C all alone, and we can solve our number problem on the left. So we push in 70.4. We're going to divide. I'm going to use parentheses here so my calculator doesn't get confused at what I'm telling it to do in the denominator. I'm dividing by 16 times 22, but I'm telling my calculator with parentheses that I want both of those numbers to be in the denominator. I get 0.2 for my C value. And the units for that would be calories per gram degrees Celsius. Okay, so we answered this first question. What is the specific heat? Well, it's 0.2. Here we have a follow-up question. Can we apply this to figure out what material this is based upon the specific heat value? Well, I think we can. Let's go up to this table And luckily, our 0.2 matches the specific heat value for glass. So it's kind of cool that you can work backwards and figure out what material you are working with. You'll be doing something very similar to this in lab, and hopefully you'll be able to get close to a known value and determine what you're working with.